This recording will show you how to use the normal distribution to approximate the binomial distribution. This example uses a normal distribution to approximate the probability that at most 12 out of 50 patients will get a headache from using a certain kind of medication if the probability is 0.22, that any one patient will get a headache from using the medication. Now, if you look at this problem, this is actually a binomial distribution problem, because if you let x be the number of patients who get a headache after medication, then out of 50 patients, the number of patients who will get a headache will be 0, 1, 2, 3, 4, 5, 6, up to 50. And this is binomially distributed with n and p, where n equals 50 and p equals 0.22. The probability that a patient will get a headache. So the probability of x equal to small x here is ncx p power x times 1 minus p power n minus x. If n equal to 50 and p equal to 0.22, I get this probability of 50 cx 0.22 power x 1 minus 0.22 power 50 minus x. And we are looking for the probability of at most 12 out of 50 will get a headache. So we're looking for probability of x less than or equal to 12. And this is equal to sum of probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2 all the way to probability of x equal to 12. Altogether, there are 13 terms. Let's review about the theory of this normal distribution to approximate binomial distribution. We know that we can use normal distribution to approximate binomial distribution if n, the number of 12, is large. So when n is large and the probability of success is close to 0.5. In fact, normal distribution with the mean mu equal np and standard deviation sigma equal square root npq can often be used to approximate binomial probabilities when n is not all that large and p is different quite a bit from 0.5. Note that the normal approximation to the binomial distribution should be used when np greater than 5 and nq greater than 5. And in the process, you have to do some continuity correction, which I'm going to illustrate using this example. So, the probability of x less than or equal to 12 is the sum of probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2 all the way to probability of x equal to 12. We know that this is approximately normal distributed mu sigma square, where mu equal to np and sigma square equal to npq, which is n times p times 1 minus p. Putting n equal to 50 and p equal to 0.22, I get mu equal to 11. So we notice that n times p is greater than 5. And also n times q is also greater than 5 as well. So we can use normal to approximate binomial distribution. And we find that from the sigma square equal 8.58, so sigma equal 2.93. Now when you do the approximation, we have to make an adjustment. So the probability of binomial random variable less than or equal to 12 are approximately equal to probability of for normal random variable x less than or equal to 12.5. This process is called continuity correction. For example, for binomial variable, probability of x equal to 5 is approximately equal to probability of x between 4.5 and 5.5. The probability of x equal to 11 is approximately equal to the probability of x between 10.5 and 11.5. And probability of x equal to 12 is approximately equal to the probability of x between 11.5 and 12.5. Therefore, when you find the probability of x less than equal to 12. This is approximately equal to the probability of x less than equal to 12.5 after continuity correction. Let's use the normal approximation now. So if mu is 11, sigma is 2.93. Probability of x less than equal to 12.5 is equal to probability of z less than 12.5 minus 11 over 2.93, where z equal to x minus mu over sigma, where mu is 11, sigma is 2.93, and we find out this is probability of z less than equal to 0.51. So now we check the table. What is the area less than equal to 2.51? We know that the area on the left side of 0, this is half of the probability, and we know this area is 0.5. How about the area from 0 to 0.51? Now we check the table over here. So look up for 0.51. So we find that 0.51 is z, and the area is 0.1950 from 0 to z. So we know that this area is 0.1950, so we put it there. So area is 0.1950. Therefore, the total area we are looking for is the yellow part is 0.5 and the green part is 0.1950. Total will be 0.6950. So we conclude that probability that at most 12 patients get headache after medication is approximately equal to 0.6950 by using the normal approximation.